Now we're going to look at nuclear power. Now, nuclear power has nothing to do with alpha, beta, or gamma decay. Nuclear power is something different. This is due to nuclear fission. This is when you have a nuclei, sometimes we describe them as atoms, these split. This is called nuclear fission, it's the splitting of nuclei, or there's nuclear fusion, which is where the nuclei join together. Now, when this happens, this nuclear energy that is locked or tied up in the nucleus can be released, and we can use that energy for good or for bad purposes. First of all, to get this to happen, we have to have what's called artificial transmutation. What this means is that we fire some very small nuclear particles at the nucleus. These particles are absorbed by the nucleus, and then they become suddenly very unstable, and then they basically split into two roughly equal pieces, and they release lots of energy. This is nuclear fission, otherwise known as splitting the atom. So, by firing particles at the nucleus, it becomes unstable and splits into two fairly big chunks. Here's an example. We have a uranium nucleus, and we fire a neutron at the uranium nucleus, and you see that it absorbs the neutron, then wobbles a little bit because it's unstable, then splits into two pretty large particles. There's nothing to do with alpha or beta particles here. Joins together, unstable, splits, produces barium and krypton. So when this happens, it releases massive amounts of energy. Where does this nuclear fission occur? Well, we basically make it happen in power stations and in nuclear warfare. Now, this is basically what happens. We have the uranium nucleus, and this is the first stage. We have basically two stages. Artificial transmutation, which means we fire a neutron at the uranium. Then it becomes a new nucleus, which is uranium-236, because it's 235 plus another neutron, which is very unstable, and due to that it splits, and that's when you have the fission. So in this case we have barium and krypton are produced, and two neutrons. The interesting thing is that these neutrons can go on to cause further fission of other uranium atoms and other uranium nuclei. Now the interesting thing here is if we had the mass of these particles, we have 235 and 1, you add this mass together and it ends up being 236, of course. Let's look at the products. The mass is equal to 144 plus 90 plus 2. Now, is that going to be equal to 236? Is it going to be more than 236 or less than 236? When we actually add them together, it makes less than 236. This is really weird. Some of the mass has disappeared. It's vanished. And this is a bit disturbing, really, because this should not happen. So this mass that disappears is called the mass defect. So mass has disappeared. Where has that mass gone? What has it turned into? So this is what we have. We start off with 236. We lose a tiny amount of mass, and that basically turns into energy. So this mass turns into energy, and mass and energy are related by the most famous formula in science, which is E is equal to m times by a constant squared, which is the speed of light squared. So E is equal to mc squared. It means the mass that disappears in a nuclear reaction gets turned into this amount of energy. This was predicted in 1905 by this young man. That in this picture, but he was a young man when he did this. So nuclear fission, let's visit it once more. The neutron is fired into the uranium. It absorbs the neutron, unstable, splits, and produces two other nuclei. Notice that these two neutrons they will go on and embed in new nuclei and will cause those to fission. This is what happens. The first fission produces 2 neutrons, causes 2 fissions, produces 4 neutrons, produces 8 nuclei, and so on and so forth. So this cycle increases and gets faster as more nuclei are split. So the neutron that is produced causes further atoms to split, and those cause more atoms to split, or nuclei to split, and this is called a chain reaction. Now here we have a nice graphic. We can show this to you. Let's have a really highly dense material. What I'm going to do is click on this, and you'll see it split, produce 2 neutrons. Those 2 neutrons are going to cause further fission. What happens when we have a high density? There was 1 left, 1 didn't fission. Let's try again. So this is nuclear fission. Now we're going to look at nuclear fusion. This is when 2 nuclei don't fission, but they fuse together, they join together, and we get it with very light particles. Here we have deuterium, which is an isotope of hydrogen, and tritium, which is another isotope of hydrogen. Let's see what happens here. They join together, fuse, produce lots of energy, and basically makes a larger particle from the 2 smaller ones. Actually produces another particle. But this is not alpha decay, this is a new product. It's basically helium that's been produced. So where does nuclear fusion happen in nature? Well, we would like to be able to produce this in power stations because it's a fairly clean way of making energy. However, it's very expensive to do, so far it's not feasible. But it does happen in stars. It's basically where all the energy from stars comes from, nuclear fusion. And we'll look at that again. So we have deuterium and tritium. The mass before is equal to 2 plus 3 is 5 units, and afterwards we have 4 plus 1. Now is this going to be 5 units? Is it going to be greater than 5 units or less than 5 units? It's actually less than 5 units. And why? Because some mass is destroyed, some mass is turned into something else. And what is it turned into? This mass defect is turned into energy. M is equal to mc squared. So to summarize, nuclear energy. This is when the energy stored in the nucleus of atoms is released, and it's when the nuclei are joined together or they split apart. Then they produce lots of energy, basically because of the mass that is annihilated. What is nuclear fusion? Fusion is when small nuclei are joined together to make larger nuclei and produce energy. Nuclear fission is when large nuclei are split to make smaller nuclei, and this also produces energy.